Hello and welcome to Thursday's edition of Cracking the Cryptic. Do not adjust your screens. Do not adjust your screens. This is the puzzle I'm going to try today. You may be looking at your screen saying, but hang on, that's a very small puzzle. I totally agree with you. And when I first opened the puzzle, I was convinced I'd been sent the wrong link. And I went back and checked. And no, this is a puzzle that... It's such an original idea. It's called Think Outside the Box. It's by Frippe. I might be saying that incorrectly, actually. I've got no idea. Frippe? The basic idea, I think, is that this 3x3 is part of a bigger puzzle. But we don't know where in that puzzle it sits, a part of a 9x9 puzzle that we can solve, even though we are only given these, well, we're not even given the digits. We're given 9 cells with some arrows and some cage totals. It's incredible. It's absolutely incredible. I found it on Logic Masters Germany, where it's got 4 stars out of 5 for difficulty, and quite a low approval rating. But we have learnt over the years on the channel to basically ignore the approval ratings because there are unfortunately trolls that exist on Logic Masters Germany who downvote puzzles. And one of the testers, who's been actually working with another tester on this on the rules, I think, thinks this is absolutely brilliant. So I am very, very happy to have a go at it. I will say, I absolutely love the idea of it. And on Logic Masters Germany, Juggler, the very Michael Lefkowitz, who is an incredibly innovative constructor in his own right, says something like, "I wish I'd made this puzzle." And yeah, that's all basically you need to hear. Now, the other good thing about this, when I say the good thing is it's original. The bad thing is there doesn't seem to be much given information. But another good thing, is that there are indexers involved in this. And after yesterday's escapade with that miracle Sudoku that I tried by Shady Moon, which is a fabulous puzzle, by the way. Yeah, do check that out if you haven't seen it. I'm going to rely on my brain being index ready, and we'll see how we get on. I'll read you the rules of this in a moment or two's time. Quite amusingly, I've noticed that that you can click around the grid here because we don't know where this is in the grid. So the grid can go up there or down here. So there's a 9x9 Sudoku somewhere within all of, within that sort of border, and maybe extending as far as that border. And that's what we're going to have to work out. So fantastic idea, very original, and I'm really looking forward to having a go at it. Oh, now I should warn you that, as usual, my car is in the garage today, hopefully being mended. So I may get a phone call at some point during the video, as nothing I can do about it. I don't know whether they'll phone me during the video or not, but if they do, then I will have to take the call. What else can I tell you about? Oh, it's the closing date of our competition, our monthly competition over on Patreon. This is the Paint by Numbers Institute. Let's have a quick look at the count. Where were we? We were at 1,190. So let's reload, and 1,700. So I've only had a few more people try it. And about another 30 have got through the final puzzle. It's absolutely phenomenal numbers. Over 1,000 people have solved the whole thing. Are you my mama? Paint by Numbers Institute. Take about all of you. Panthera, Alithana, Haleb. Is that Jalab or Haleb? I'm not sure. And the Asylum. And well, actually Clocksmith as well for the artwork. Absolutely brilliant stuff. Yeah, well, it's over there, and today is the closing date. We're very flexible about that in terms of time zones, but do try and get your entries to us fairly soon if you want to be in with a chance of winning the competition and making a Sudoku video with me. Oh, something to mention on that. So I did do this collaboration video where Bismuth, the YouTuber Bismuth, and I solved a puzzle. I'm going to just tease and let you know that I'm hoping in the coming weeks to solve a puzzle with Chain Bear, the Formula One YouTuber, and Kurt Hugo Schneider, the sort of polymath music guru who's been with the channel for such a long time, and hopefully more too. So if you have a YouTuber that you'd like to see solve Sudoku with me, and you have a way of contacting them, do let them know that we're on the lookout. And you can drop us an email at crackingthecryptic@gmail.com as well. Now, I think that's everything. Let's have a look at my birthday list. Hebe, you turned 29. I think that's such a beautiful name, Hebe. Your partner Seb wrote to us and said that you both often watch before bed. So I hope, Hebe, you have a great birthday today with, of course, a large slice of heavily iced chocolate cake. Next, John. John, you are from the Basque country. I have been to the Basque country many years ago. And you're turning 47 today. Many congratulations on that. I know this because your friend John wrote to us and said you might appreciate a shout out. So John, I hope it's a great birthday. Next, Sarah. Sarah, it's your birthday. And I know this because your partner Carlo wrote to us. And I have the impression from Carlo's email that, Sarah, you got Carlo into Sudoku and cracking the cryptic, and he's now hooked, which I fully approve of. And he likes to solve rather than doom scroll. I think it's much better for your sort of well-being to solve Sudoku than doom scroll. I will say that. And Sarah, I hope you have a great birthday today. Oh, and this last one is not a birthday, but it's a 8.5-year anniversary for Becky, whose husband Matthew wrote to us. And now, can I read my writing? Not very easily. What does this say? What on earth have I written here? Only... Well, it's not a good sign if I can't read my own words. I know you both watch, I can see that. Oh, you've only been following. Yeah, okay, you've only been following for a month or two, but now you both watch. Okay, well, that's great. And Becky, I think an 8.5-year anniversary is plenty of an excuse for cake, so I hope Matthew provides it for you. And, well, congratulations on reaching 8.5. And with that said, this is so strange. It's so strange looking at this. Let us have a look at the rules of Think Outside the Box, which we're definitely going to have to do, by Frippe. They are as follows. Normal Sudoku rules apply. Well, okay. This 3x3 of cells are a part of a standard 9x9 Sudoku grid and can be located anywhere in the grid. So is it really true? Oh, I see. It probably is. Is that? Oh, okay. So is that a 9x9? 4, 5. Yeah, okay, so that's really cool. Okay, so this could be the top left corner of the grid, or indeed the bottom right corner, or the bottom left, or the top right. Fill the 9x9 Sudoku with digits from 1 to 9. Okay, with normal Sudoku rules applying, presumably. Digits in a cage cannot repeat and must sum to the total in the top left corner of the leftmost cell in the top row of the cage. All cages have a cage total. Okay, so that's saying that... Okay, so you can see there's a 45 cage. That's an interesting number. Did you know that 2025, which is this year's year, is 45 squared? I'm sure you did if you've been watching the channel. That's 24, so that's part of a 24 cage. Okay, so what we get, let's just deal with that. That 24 cage can't do this, is one of the sort of implications of that rule. I hope that's not solving to tell you that. It's just what the rules say. The rules say that this, the total, the total for the cage is in the left the leftmost cell of the top row of the cage. So if this was the cage, the 24 should have been given here, and it's not been, it's been given there. So that is something we're going to have to bear in mind. NB, the very bottom right corner of the given 3x3 cells depicts a cage corner, which is there but difficult to see clearly. Oh, right. Okay, so yeah, I can just about see that. I'm just checking which glasses I've got on. Yeah, no, it is there. So I can see that. I don't even know how to describe it, but if you look in the bottom right-hand corner of the grid, there is a sort of cagey type thing there. So I think, so actually, well, I hope this isn't solving as well. Yeah, that rather suggests that that is part of the grid, but not in that one's cage. Anyway, we'll get to that in a minute. Now, digits along an arrow sum to the digit in the arrow's circle, located at the opposite end of the line to the arrow tip. Arrows do not touch or cross themselves or other arrows, and two arrows never enter the same cell. Arrows do not branch, and only one arrow emanates from a circle. Okay, this is okay, so let's just draw an arrow in. I'll draw an arrow up here. So this is an arrow. And I think what this rule set, let's draw another arrow over here. What is this rule set saying? It is saying that, so it's saying normal rules. So those two digits, so say these were 1 and 2, that would be a 3 because 1 plus 2 equals 3. That's one of the things it's saying. Digits along an arrow sum to the digit in the arrow's circle located at the opposite end of the line to the arrow tip. Okay, well that, I suppose, is that trying to emphasize that this is an arrow tip or something? I'm not sure. Arrows do not touch or cross themselves or other arrows. Okay, so we can't sort of take these arrows up and join them together or cross over them or double back on ourselves or anything like that. And two arrows never enter the same cell. Okay. And one thing is it's saying we can't do that, can we? We're saying that each circle has one arrow. Yeah, I think that if I do manage to solve this puzzle, I may slightly amend the rules there just to make that a bit clear. I mean, it does. That's what it says. I just think it could be expressed slightly more succinctly. Now, here's the kicker. This last rule is a kicker. It says the entire grid operates as row indexes, which is in inverted commas, i.e. digits in row X indicate the row in which the digit X appears in that column. For example, if row 3 column 6 is an 8, but I can't show you row 3 column 6 because I don't know where it goes. How can we do this? Hang on. Let's imagine that's the very middle of the grid. So that's going to make the grid look like this. Okay. Oh, that's so strange. Okay, so if this was the grid, what we are told is that row 3 column 6, which would be that digit, if that is an 8, row 8 column 6 is a 3. Row 8, that digit is a 3. Now why is that true? Okay, so the entire grid operates as row indexes, i.e. digits in row X, so this is row 3, indicate the row in which the digit... Oh, yeah, okay. So this is just like yesterday. But it's the sort of... It's the horizontal lines that we were looking at yesterday. So this 8... So everything in this row is talking about the digit 3, because this is row 3. So if this is a 1, that's saying put the 3 in this column in row 1. If this is a 9, it's saying put the 3 in this column in the 9th row. So this being an 8 says put it in the 8th row. So that's how it works. But that's going to work for the whole grid. So this row, for example, is going to index 6s. So if that's a 7, that's a 6. If this is a 1, that's a 6, etc. So hopefully that's clear. I don't know. Oh, I'm going to have to do this manually. It's just so strange. Anyway, they are the rules. I do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. Now there are some things I can see straight away here. That 45k. Well, let's deal with the secret. Now that's something I share with only my very favourite people. But if you're watching this video, you're definitely one of my favourite people. The secret is, of course, that all 9 Sudoku digits sum to 45. If you add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, you get... Hopefully I didn't miss a digit there. You get 45. Now, because digits can't repeat within cages, that means that 45 is part of a 9-cell cage that contains every single Sudoku digit, as indeed is that one. So we better give these colours, I think. Should we make that one blue? I think blue and orange. Phone is buzzing, but that's not a phone call. So... And 28, so that's got to go there, doesn't it? What colour should we have for that one? Purple, maybe? And then we've got another cage here, but I just want to... Yeah, okay, actually this cage is a different colour to all 3 of it. It's clearly delineated from all of these other cages. This one has to grow and go there, doesn't it? In fact, the blue one, you can see there's no grid furniture on the right hand side of the grid there. So I think we can do at least all of that and possibly more. Yeah, the 45 has to grow again. So we're growing a bit this way. And this cage is going at least to here. Well, it's not actually stopping there, though, is it? Because it's not got a total in it. Yeah, that's interesting. This cage has to get up at least as high as this again. 1, 2, 3, 4, 5. This digit is definitely not in the green cage because of the... Again, there's sort of some cage furniture, isn't there, on the west side of the grid here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we don't know. We don't know where this cage goes. But at some point it's going to have to come at least as high as this and possibly higher. I think it can get higher. Because it's got... Assuming this was part of a 45 cage, it could contain 9 cells, so it could go straight up and reach this row, which is where the 45 would be. But this isn't fog, is it? Oh, this is really weird. For some reason, my brain is saying to me, oh, you'll find out, you know, what the total is for this cage. But now I'm suddenly realising I won't. It's not that there's fog here that will suddenly be revealed to tell me what this cage total is. No, literally all you get is this 3x3, and we're going to have to build up everything off the back of it. It's such a remarkable idea. You know, I wonder whether... No, okay, I was about to say, is the entropy of the indexing going to be important? What do I mean by the entropy of the indexing? This is even hard to explain. Actually, it's really hard to explain. But basically, I will be able to explain it once I can draw a grid. Let me just try and draw a grid again. If that's the middle, so it would go there, wouldn't it? I think. This is so crazy. Okay, so look, I'm just going to quickly sketch in. It's like being back on number file. I've got to quickly sketch in a grid. Let's imagine that's the grid that we're going to find in this puzzle. What I want to talk about is these 3 digits, just for a moment, and talk about entropy, because we're told that everything in the grid is acting as a row indexer. So this is row 1 of my invented grid. So every digit we put in here is basically telling us the row in which the 1 will go. So if this square was a 5, then that would be saying write 1 into that square. If this square was a 6, you'd write 1 into this square, etc. Now, something that we're going to have to bear in mind is that these 3 digits, because they can't index 1 into the same box, imagine this was 5 and this was 6, that would be a problem because we get a 1 in both of those positions, and that's going to break Sudoku rules in this box here. So what we're going to find is that these 3 digits include one low digit, which is basically going to index the 1 into that box, one middly digit, which is going to index a 1 into that box, and one high digit, which is going to index the 1 into this box. So, but that's going to be true in this puzzle for every single collection like this. Every one of these little horizontal triominoes I'm drawing is going to have that property. So the grid is going to be very heavily constrained once we discover where it is. But unfortunately, that is something that we don't know yet. Oh gosh, it actually feels like we've really taken a step backwards now. So what are we doing here? See, could that be... absolutely, it could be orange, couldn't it? I was going to say, can we label this cell another colour? Because we know it's not blue because of this funny rule about the bottom right having this corner thing in. Oh, I see. Right, okay. So we've got a very hefty arrow here, haven't we? Because this cell that we've got, now I can draw this. This arrow, or this arrow's going there and this arrow's going there. Now, ordinarily, I would immediately have gone circle here and expected there to be 2 arrows emanating from that circle, but we're expressly told in the rules that there is only each circle has 1 arrow emanating from it. So there's some impossibly difficult, I say impossibly difficult, I mean, I now can tell you that the Sudoku I just drew with this as box 5 is incorrect. Because if this was a Sudoku box, every one of these 4 digits would be different. They would add up to at least 10 if they were 1, 2, 3, and 4. And wherever the circle goes, wherever the circle from this arrow is, it would be a double-digit number, which we obviously can't put in. So these cells are going to have to be... Well, they're going to have to be almost too small, aren't they? Because there's another digit to come here. We've got 1, 2, 3, 4. We've got 5 arrow cells. But I mean, if that's the circle, then you can see we haven't discovered the arrow tip yet. So there will be another cell on the arrow here, and that would be 6 arrow cells that would have to have an average value no higher than 1.5 in order to keep the circle down to having a value of 9. No, that's wrong. No, it's right. That's right. Okay. This is not an arrow cell. That's a circle. That is definitely a circle. Now, the reason is, let's imagine that wasn't the case. Let me try and draw that down. Well, what I'm seeing there is those 3 digits are all different. So let's minimize them. 1, 2, 3. That's the minimum we could put onto these squares. 1, 2, and 3 add up to 6. The minimum value of those would be 1 and 2. That's now 9. And this can't be a value of 0. So whatever it is, wherever the circle is, it's going to be a double-digit number. And that won't work. So this square has to not be. It has to be a circle. It is the sum of this long arrow, which. Okay, so now that cell here, I suspect that has to be the arrow tip. I mean, I'm not. Let's think about this. So now we've got 1 plus 2 is 3. Another 1 plus 2 is 6. 7, 8. Oh no, that's really weird. That could actually. I mean, there's probably a technical reason why you can't do that, but I think that could actually be 8 and not even 9 now. Could we put? No. Okay, so these digits are either 1 and 2, or I'm going to say 1 and 3. I don't think they can be. They can't be. They definitely can't involve a 4, because if this was 4 and 1, that's 5. Plus another 3 is 8. Plus another 2, if I put 1 there and 1 there, that's 10 again. So these are from 1, 2, and 3, and that logic must preserve to there. But I'm not sure. I think it's the same principle, isn't it? If there was no 1 in these 2 cells, they would be a 2, 3 pair, that's 5, plus a minimum of 3 there, that's 8, plus 1 is 10. Right, so, I see, right, this is beautiful. This is a beautiful, so elegant. Okay, so now I've deduced that one of those squares is a 1, and I've deduced that one of those squares is a 1. But that means the pattern of 1s in these 4 cells is either this one and this one, or this one and this one. And, well, that one is not possible. Because if you do put 2 1s there, look at this little cage. It's got 2 1s in it. You can't repeat a digit in a cage. So that's wrong. So these are 1s. Oh, now beautiful. Right, now I can't make both of those 2s. Because they're in the same cage. So they are adding up to 5. So we're on 5, 6, 7, 8, 9. That's beautiful. What a lovely, lovely series of sort of constructing points there. So this is a 9. I've got loads of digits now. Now. So all I've got to do is work out. Okay, I've got 4 1s here. They can't all go. Right. Okay. So what I'm trying to do is envisage in my mind where I can divide the 3x3 boxes, and okay, let me think. If that's clearly impossible, isn't it? It's not possible that this is one of the sort of 3x3 box delineators in this puzzle. And the reason I think that's true is that if I was to draw this line, where am I drawing the vertical lines so that I don't end up with 2 1s in a box? I clearly can't draw it there, because that's going to put 3 1s in a box. I can't draw it there, that puts 2 1s in a box. And if I draw it there, that puts ones in that box. So this is not a line. So there's sort of an X going along there. Now, we just have to repeat that trick again. So okay, so does that trick also, so that the corollary of that is that this isn't an X line. Because if that is an X line, if we drew this horizontal line, obviously we'd then have to draw another horizontal line sort of 3 boxes down, wouldn't we? So this is also not a delineator. So either this, I don't think that's going to work. Am I wrong? I don't think that works, does it? Because if you draw this one in, again we've got the same problem. I've got to draw some vertical lines now. I clearly can't draw one there because those two ones would be in the same box. If I drew this one, then these ones are in the same box. And if I drew this one, then those are in the same box. So, okay, so this doesn't work either. And that's perfect, because now, if all of that is true, there must be a delineator somewhere, and that is there now. So that is forced to be true. And okay, so now I've got to be careful. So I now can't do that one. That's impossible, because that's going to put this one in the same box. So that's not in. And then we go 3 away. That's not in. So we can draw some more X's down the grid. I'm sure there's a sort of better way of doing this, but this is going to be my way of doing it. So now, how do we do it? If this was a line, then I'd have a problem here, wouldn't I? So that isn't one. And then we can go 3 away. 1, 2. So this isn't one. So now I think, is it forced to be this one now? Seems to be. I think that's, oh, not that, no, or that. That's definitely not what I'm trying to do is that. Given that I've got to have a 3x3 box, and given the X's I've put in, I think we're now looking at this. So now I get to draw, look, hang on, let's make sure I don't put this in the wrong place. Is it that? And this? And this? Oh, this is so clever. Right, that's in a box. So that, right, look at that. So once we draw that one in, we can sort of narrow down the parameters of the grid, because we can't go. We know that the grid is only 3x3 boxes wide, so we can draw that one in because the grid will be a square in the end, and we're either going up here or down here. And most of the rest of this then is sort of totally unneeded, isn't it? We can colour these in or something. That's exactly what I'm planning to do, by the way. How far over did this get in the end? Oh, it got quite close to the edge, so all of those squares are not used. And look, we can do better, because all of these are not used. That top row is not used. So we're trying to just sort of narrow it down now within quite a slim area. Let's draw another black line up there. So there's one of 2 Sudokus. It's either this Sudoku. Oh, hang on. Why does it do that? I don't know. Or it's this Sudoku. It's one of those 2 things. Now, okay, now let's get rid of the X's, because they aren't serving any purpose, are they? We know where the box borders are approximately, so we might as well clean that up. Now, trying not to sneeze. Ooh. So imagine this is the top of the grid. This 1 is saying that this would be the row 2, wouldn't it? So it would be saying that 2 would go there. And that is saying that this arrow, well, it would be saying that's a circle. Because if this arrow, say, went to there, none of those 3 digits could be lower than 3. And actually these two would have to be different. So we'd have 3 plus 4 plus 3 as the minimum total for the arrow, and that's already 10. So I think if this is the top of the grid, we're going to run into problems. The only way that's the top of the grid is if this is a circle. Oh, wait a second. Hang on. No, forget that. These 2 digits, one of those is high entropy. Remember what we said about the 3-cell sequences? They always have to have a low, a middle, and a high. Well, if this was an arrow, it doesn't matter where this is in the grid. Because if that's an arrow cell, one of these is high entropy, at least 7, and the other would have a medium entropy, at least 4, and 7 plus 4 plus this digit is way more than 9. So this is a circle. Sorry, that's totally obvious, isn't it? That is a circle. And therefore this is the high entropy digit in this 3-cell sequence, because we can't add a high digit and get a total which is a middle digit. So that's a 4, 5 or a 6. This is a 7, 8 or a 9. So this digit is a maximum of 5, 4, 3, 2. And is there some way that this 2-3 pair sees this cell? Because if it is, that's going to make that a 9. I'm not sure. Hang on. Let's go back to the green. This green cage has to get up at least as high as whatever row this turns out to be. Its total is going to be it's at least this high. How does it get that high now, given all of this space is not available? It's got to go up there. 1, 2, 3, 4, 5, 6, 7, 8. So it's either. Oh, I see. Ah, beautiful. Right. This cage doesn't go any further. That is the shape of this cage. This is very clever setting. Who's doing this and not liking it? It's brilliant. The reason this is the extent of the cage is that it can't have a 1 in it. There is simply nowhere to put a 1 in this green cage. So, but the cage does need to be at least of length 8 in order to get to this square and have a total that wasn't shown in this square. So the total for this cage is 44, 45 minus 1. It's got every digit in it apart from 1. I don't really have a way of annotating that, but okay, let's try Sudoku for a moment or two. The thing is, I can't really do it because I don't know whether I should be putting Sudoku ones here or here. It depends where the grid goes, and here or here. If this is the top of the grid, That one is indexing a 2 here. That would be a that would be a 3. This couldn't be a 2 anymore. Well, I don't see what the problem is there. Hang on, what am I missing here? I don't know. That digit, let me just label that A. That's in one of those cells in box, whatever box this is, in this box, because it can't repeat in green. So it's in one of those. I mean, the same is true of that digit. Let's just make that B for a moment. That digit is also in one of those squares. Okay. Hang on, let me just revisit the rules. Is there a rule I'm not remembering? We've got arrows, but I've worked out this arrow. And that's the strange thing is, there's no more arrows. It's not like fog where I might find another arrow if I'm, if I do some good solving, I get more information. There is literally, it's such a clever idea to construct an entire Sudoku out of just giving the 3x3 box. I think it's genius, actually. Now, hang about. If that's the bottom of the grid, so let's just make those squares black for a moment. Have I got enough room for 2 9-cell cages given? Oh no, I can. This can go that way. Oh, bobbins. I suddenly thought there's not enough room, because obviously a 9-cell cage is the equivalent of a whole Sudoku box, and we've got 2 9-cell cages to fit in here, and they can't fit in that space because that's only 17 cells. But I didn't see that this one could spill out here. It can't go very far that way. So if it gets 3 cells, 8 cells, 9, it would be that shape. And then this one can't go up here because this is where its cage total is. So it's never going up. Oh, hang on, there's a 24 cage here. Where's that going? Yeah, this is well, those 2 squares don't add to 24, do they? It's got to go there. It can't go up because this is the top leftmost cell in the cage. And this is not a 7. So this can't be 7, 8, 9. It's impossible. So that's got to be in it. Now, that's nearly impossible. 24, 25. Right. This cage, I'm not sure where it goes, but it doesn't go there. So this, right, this is a new cell. I know it's a new cell. I mean, it might not, well, no, it can't be caged because there are no cages. Oh, well, this is a cell that is not purple and is no other colour that I have in the grid. So let me make that a different colour. I'll make it red, shall I? It's a bit close to purple. I might make it, no, indigo. I'll make it, that one can't go up. Yeah, I'll make it indigo. Because, imagine this was purple. Now, if this is purple, these digits here sum up to a maximum of 24, possibly less than 24 if the purple spills down here. But the maximum size of those is 24, so let's assume 24 is what we get. Now the maximum size of those squares is 4 if they're a 1-3 pair. So the absolute maximum size of those cells is 28, which is just possible if these two squares are an 8-9 pair, to make sure that the row overall can add up to 45, which we know it will. But these can't be an 8-9 pair, because if these were an 8-9 pair, we'd have 2 digits of the same entropy in those 3 cells, which we know does not exist in the puzzle. So that square is not purple, and I'm going to make it indigo. That doesn't now mean this has to turn down, though. Those could add up to 24. So I feel like that one being orange is very difficult. Is that true or not? If that's orange, blue would have to take that square, because it can't get to 9 cells if it only takes those cells. 1, 2, 3, 4, 5, 6, 7. Oh no, that's easy. It can do it. Oh, of course, and this is all on the hypothesis that this is... Oh, is that... No, hang on. That 24 deduction, that might be independent of this being the bottom of the grid. Yeah, that is independent of that. So when we unwind this, if we unwind it, this deduction that these are all purple survives, because that was nothing to do with cramming digits into the bottom of the grid. Hang on a moment. I might be able to demonstrate this isn't orange. Let me think about this for a second before I make a fool of myself again. 1, 2, 3, 4, 5, 6, 7, 8. I mean, if that can that be blue as well? 1, 2, 3, 4, 5, 6, 7. No, that's so. The only way that this is orange is if the blue goes exactly to there, can't go any further, and then orange does those, and then orange would take one of those 3. But I don't think this works, because I just want to think about this just for a second longer. I don't think it works. I think there would be a repeated digit in blue, because yeah, I mean, if these are blue, so what I'm saying is, in order for this to be orange, blue's shape is forced in this eventuality where we've sort of capped off the bottom of the grid. Now, that is a problem, because those 3 digits, where do they go in box 8? And the answer is, because they can't repeat in the blue cage, they go there. So where do these 3 digits go in box 9? The answer is there. But they can't go there, because one of those digits is blue. And you can't repeat a digit in blue, but you would. So this doesn't work. So that means that this square is a new colour that we haven't identified yet. Let's make it lime green. It's not orange, it's something else. It's not blue because of the weird grid furniture thing. And it can't be orange because we've proved it can't be orange. So now, if this is the bottom of the grid, blue has to go there, because there isn't enough space for it here. There's never been enough space for it there. That's always been available. Oh, Simon, this is the height of Muppetry. Well. No, okay. Right. Just forget. All bets are off. This doesn't work. This can't work. This cannot work. Right, we're there. We're there. Sorry, and I could have got this earlier, but this square is the key. Let's just make this a digit. Let's make it the digit E. This is the digit E, and E is a problem in the puzzle now. And that is because 45 cages have to contain every single digit, including the digit E. Where are we going to put the digit E in whatever the blue cage eventually looks like? Where is the E going in it? And the answer is somewhere over here in this box, because it can't be there and it can't be there because E sees all those squares. And then here is an interesting question. So there is a blue E in this box. Where is the E in orange? There's nowhere for it to go. Those can't be an orange E because of this. And there's a blue E in there, which means that the orange E can't be in there either. But orange only lives in these two cages, or these two boxes in this world. So this is all wrong. And that means, let's go right back. I'll restore my purple, I think, but I want to go right back. This line is not drawable, which means that line is drawable. So this is all out of the puzzle. These lines don't live in the puzzle. This is the shape. Oh, no, I don't want to do that. I want to do that. So actually the puzzle has ended up sort of a bit southeast facing, hasn't it? And okay, so let's restore my purplification. I think those two had to be purple, and this one is not purple, and I made that indigo. And that was simply due to the total if this was purple. So I think that's fine. But and now we're going to lose. We're going to lose some things, but not others. We're going to lose all of my interesting logic about where blue went. But what we gain is indexing, isn't it? Because that is now in row 2 of the puzzle. So that is where 2 goes. This is in row 3, so we put the 3 in row 1. That is in row 4. We put the 4 in row 1. That is in row 5. We put the 5 in row 1. Now surely this arrow's come down now. That's not 2. That's not 5. Oh. That's a 3. So that's a 2. That's a 3. 9 is in row 6, so that's a 6. It would be so easy to make a mistake here and not pick a... Look, that 2, that's got to have a 5. That's in row 5, so it's saying put the 5 in row 2 of the puzzle. Oh dear. Oh no, that's fine. Oh, that can't be 4, because that would make that a 6, and that would be a 10. So that's not 4. It's 3 or 5. Yeah, okay, this is a 3. Because if this is a 5, it's in row 4, so it's saying write 4 into this square, isn't it? So this arrow would become 5 with a 6 above it and would add up to 11. So that is 3. Oh, and that actually works even better because that's in row 4. So it's saying now write the 4 into row 3. So I've got 3 plus 4 equals 7. And these two index... they index each other. So this 7 is in row 3, so that puts 3 there. And in box 2 we have not placed 6, 8, that's 8 by Sudoku. It sees the 6, 9 pairs, so this is a 6, 9 pair. Now let's think about the indexing. So that 8 is saying write 2 there. These squares are 4 and 7. that one. Yeah, I should probably make that the digit C. Hang on. Yeah, do you remember we made that A of it originally, didn't we? We made that B, and if I think of that as C, where does that go in this box? It's got to go in one of those squares. So those three are in those three, and 3 is definitely down here. And if 3 is down here, that's saying, right, 6. Yeah, that can't be 3. Because the 3 here is in row 6, so it's indexing a 6 into row 3, which now must be in one of those squares. So if that was 6, I see, the 3 and the 6 index each other. Oh, but that, no, hang on, that doesn't work, does it? Oh no, no, maybe it does. So the 6 would put a 3 here. The 3 would put a 6 back where the 6 was. But separately, the 6, there would have to be a 6 here as well, and that would index itself. Oh, goodness me. Because it's the 6 in row 6. Every digit is always how should I put this? There's in every row there is one digit that is correct. So think about 1 in this row. The 1 is saying write 1 into the row I'm already in. So it's indexed itself. The 2 in this row will index itself. The 3 in this row, which is there, has indexed itself because it's saying put the 3 into row 3, which is exactly what this digit has done. So in this row there'll be a 4. So there are 9 digits in this puzzle that are sort of self-indexing, is what I want to say. And that 6, if it's a 6, would be in one of those squares as a self-indexer. Now, see, that would be really cool. 6 by Sudoku is in one of these squares. But if that's a 6, that would place 6 here, which would put 5 here. It's so intricate. Right, here's a small point. Oh, no, I know what I can do. I can just do... Oh, there's loads of ways of doing this now. What I was going to say is that this can't be a 6 because it would put a 1 here, but the simpler way to have seen that would have been to note these all have to be different entropy, of course. So this has got to be high, that's got to be low. That's saying write 1 in here, the 6 is saying write 2 in here. Oh, this is fabulous. This is now medium entropy because it's got low there and high here. So that's 4, 5 or 6 indexing a 6. So it's not 4 because that would put a 6 here. It's 5 or 6. So if it's 5, that's a 6. If it's 6, it's indexing itself. And that would mean this isn't a 6. Okay. So now we don't know whether this is orange or not anymore, do we? Because blue can escape down here or go this way. Blue has got so much more space than it used to have. Right, let's try maybe this column. 4, 5, 8. Let's put in all the options and think about them. So can we rule anything out by... We can't rule anything out by entropy in the triominoes, I don't think. If that's a 4, it's indexing itself. If that's an 8, it's putting... Oh no, that's all fine. Yeah, I think these sort of... Hang on, how does this work then? Is one of these self-indexing? Is that what has to happen there? The 9 and the 1 pair off. The 3 and the 7 pair off. The 2 and the... Yeah. Okay, so in those 3 squares, one of them one of them is self-indexing. Now you may say, no, Simon, they could all be self-indexing. That is not right. That is not right, because remember what happens in the columns. So if if in the columns things pair off with each other, so we're seeing it here, 1s and 9s pair off, the 3 and the 7 pair off, so there'll always be an extra digit that you can't pair off in any column of the grid. Most of them can be paired off and there'll be one stray. Now you may say, oh, no, I could do, why couldn't you have a column that goes like this? And the fact is, you're absolutely right. Yeah, that could work absolutely perfectly. Everything is self-indexing in this column, and the world is a very sensible place for this column. But the rest of the puzzle is broken now. Because remember what we said, there's only one self-indexing digit in each row. The 1 in this row, the 2 in this row, the 3 in this row. So there are 9 self-indexing digits to play with. And if I pack all 9 of those into one column, how do you deal with this column? Is it possible to have no self-indexing digits in this column? And the answer is no, because you can pair off the digits as we did here with the 9 and the 1, but you'll be left with a rogue digit you can't pair off. And it needs, so there must be at least one self-indexer in every column. And as there is exactly one self-indexer in every row, they have to be allocated one per column. So in this column, one of these will be correct. So say that was a 4. Then actually we would immediately know that the 5 and the 8 would have to go 8 here, 5 here. Otherwise we'd have too many self-indexers in this column. Which is unfortunately, it's going to be helpful once we know which of these is the correct one. But until we know, I don't think we can do anything. Let's try row 1. 1, 6, 7, 8. And the 1 is over there for some reason. Oh, that's Sudoku. So I've got 6, 7, 8 in the corner, indexing a 1. It's not 6, because that would put a 1 here and it would clash. So that's not 6. So 7 or 8 are in these. Well, 7 or 8 means that 1 is in one of those two places. Oh, that's just hopeless. That's so hopeless. It's probably to do with... It's going to be something to do with how we grow these cages, isn't it? The 24 cage, could it go there or not? If it doesn't go there, those two digits add up to 13. And they couldn't be 4, 9. They couldn't be 6, 7. They'd have to be 5, 8 in row 3. So we get 3s there and 3s there. And that would be a 3. And that would put 2. I don't believe it. There's so many things that flow from that, but none of them break. Okay. And otherwise all bets are off, because this could travel down the grid and be a much more complicated creature. What about 2 then? Okay, so 2 is in one of those squares, which means that's indexing a 4, isn't it, into one of those. Oh, see, that's just falling out from Sudoku. I often find this with these indexing puzzles, that you think you're learning stuff, but you actually already know the stuff you think you're learning if you concentrate enough. There's now a 3 in one of those, so there's a 2 in one of those. And okay, well, that's not something we knew from Sudoku. So there is now a 2 in one of these, which is a self-referencing 2. Now, can you only have one self-referencer in a box? I don't think that's right. I think you could have a lot of self-references in a box. Although here you couldn't. because 1 and 3 would be involved, and they don't seem to be self-referencing. That 3 is self-referencing. Oh dear, come on. Let's just... I think we're nearly there, actually. We've made such a massive amount of progress. All we've got to do is just figure this out. So 9 is in one of those. So that means this square is 7, 8, or 9. Because if the 9's there, it's indexing 7. If the 9's here, it's indexing 8. If the 9's there, it's self-referencing. And that made sense with entropy as well. There has to be a high one there, so we could have just written that in. Thing is, this 45 can go almost anywhere. It's got once we remove the floor of the grid, everything becomes a lot more flexible with these cages. I think maybe it's this one. I know that adds to 44. It's got to have all the digits in it apart from 1. So okay, the 9 in this box is in the cage, isn't it? It's in one of those squares. So whichever one it's in, it's indexing a 3 or a 4 or a 5 down here. So if that digit was the high entropy digit in this string, it wouldn't be 7 and it couldn't be 9. It would be an 8 into this square. And that 8 would be indexing a 3 into this square. Yeah, and the 3 and the 8 are pairing off then. So that's 8 in that example. But if that is not high, if that's middly, then it is 6. So that is 6 or 8. It's 6 because of Sudoku. If it's middly, it can't be 4 or 5, and if it's high, it has to be 8. So that digit is 6 or 8, and that digit then by green logic is in one of those squares. So these squares here are 6 or 8, which is not in that one, because what we're saying is this digit needs to appear in box 4 in somewhere in these two positions now, because it can't repeat in green. This one has to be here somewhere, and that has to be in one of those two. And then I think this one as well has to be in here somewhere. But that's under much less pressure. So the 3 is the low digit. We don't know. 4 or 6 is the middly, and 7 or 8 is the high. And that pencil mark there is one of the most atrocious things I've ever seen in my life. Okay, that's not 4. This isn't... No, we can't limit it. Oh dear. Okay. What do we say about the top row? 1, 6, 7, 8. 1, 6, 7, 8. And so 1 is being thrown down the grid into sort of this bundle of positions. 1 and 6 is definitely over here. Oh, but that's just mimicking this. This is exactly what I was saying. You learn things you already knew. Ah, okay. 4, 7 would. Ah, of course. Yes. Oh, sorry. Look here. Look at this column. If that's 4 and that's 7, I've got two self-indexers in a column. We can't have... In fact, we'd have 3 self-indexers in a column, because that 3... right. Sorry, what I should probably do is keep track of self-indexers. Let's use the pen tool. I'll just give that... I'm just going to ring that because it's a self-indexer in a column, and I can't have any more self-indexers in this column. There's 1 per column for the reasons we discussed before. So this can't be 4, and that means that we get the 7 and the 4 in that order. That's not 4 anymore. This can't be 8 now by entropy. This has to be a high digit by entropy. Surely that does something. Okay, so one of the options for that was 4, wasn't it? So 4 is coming out of these squares now, because we definitely have to have a 7 down here, and the 7 is indexing a 6 into one of those 3 squares, which means 6 is in one of these 3 squares, which means that 8 is in one of those squares. But how can that be? How can this be doing this? Because that's going to fix this digit. I don't understand. I really don't understand how that can be so profoundly. Let me think about this again. I've proved 7 is down here. That does index 6 in here. Sudoku tells us 6 is here. That's row 8. So 8 is now in one of these 3 squares, which means 8 is not in these squares at all. So this can't be 8, because it would put an 8 here. So that has to be 6. Now, if that's 6, that means that is not 6, which means that is not 7. That has to be 3. No 3 in the corner for us. This is a 6-7 pair. The 3 and the 6 index each other. That's exactly what we were looking at earlier on. 3 is in one of those squares, indexing a 5 into one of those squares. Oh no, we've done that. We've got 5 in box 1 already. 3, 6, 7 makes this a 5. That's indexing 6 into here. 5 means this is a 4 and this is an 8. And now we've got to... Oh, that's a 5. Okay. Oh, bobbins, and look, that's just a panoply of 1, 2, 3, 4, 5, 6, so it's not going to affect these digits at all. These are just a 7, 8, 9 triple. Well, we've just got to be careful. Have we had the self-indexer? No. No, we haven't. So one of these exactly is a self-indexer. That's a self-indexer. And I hope there won't be another one in this column or I've made a mistake. No, that's fine. Okay. Let's see if we can find any other self-indexers. Well, the fact is I haven't got enough digits in the grid to be able to avail myself of that. Right, we know what these digits are now though, don't we? They are 4, 5, 8, 9. Let's put them all in and see if we can eliminate things. We can eliminate 8s from there. 4's from here. 4 is there exactly. So that's in the fifth row. So that's a 5. This is now a 9. And this is an 8. Now that's got to be good stuff, hasn't it? 8 is in row 4. So that's a 4. 4 goes down here. That's in row 9. So oh, see, it's just Sudoku sort of filtering its way through. What else did we get over here? We've got a 9 here, putting a 5 here. So 5 is over there. That's putting a 7 into one of those squares, which again this is all available from Sudoku. 3, 7, and it must be a middly digit, which is 5. So this is 2, 9, and it must be a middly digit, which is 6. And this is 1, 8, and it must be a middly digit, which is going to be 4 by a process of elimination. And this column needs 6, 7, and 9. So let's put that in. 6, 7, 9. That's not 6. So that's 7 or 9. Indexing the 9 either into its own position or to this position. Have we had the self-indexer here? No. Don't think so. What about then? Well, what do we do? What do we do next? The 4 and the 5 index each other. The 3 and the 6 index each other. What about row 3 maybe? This square is an 8. It's a naked single, I think. I've got 2 and 5 here. I think that makes this 8 or 9. And it can't be 9. That is 8. And that's in row 3. So that's a 3. These index each other. There's a 3 down here. That's putting a 9 into one of those squares, which makes sense because that's exactly what we'd expect. 2, 5, 9. That's a 7 by Sudoku. That's putting a 1 here. I'm slowly getting there. These squares are a 2, 9 pair. Oh, that's all. That's done. Right. 9, 2. 9 puts 2 here. That should complete this column with a self-referencing naughty old 8 there. Okay. That is self-referencing. That's a 2 in row 2, so that's quite cool for this digit, which can't be a 6 now because it would be self-referencing. So those go in that order. That puts 6 here by Sudoku. Ah, and that's helpful here, look. If that was 7 and that was 9, we'd have 2 self-indexes, which we mustn't have, so they must be the other order. And I don't know if that, I presume, well, it does mean that there should be a the 6, I was going to say there should be a self-indexer in the column that we haven't yet located. Right, so 8 comes out of here, 9 comes out of here, 7 comes out of here. And now, is there an option here that's going to result in more than one self-indexer? If that was 7, no, that wouldn't put 9 and 8 in the correct positions. If that's 8, that would be 9. No, that wouldn't work either. Bobbins. All right. What about these digits? These are now 1, 6, and 8, indexing 1s. So 1 will index itself. 6, I see that's we've just got that already. 3, 4, and 7 here, indexing 2s. So there is a 2 in one of those, which again Sudoku would have told us. Oh, right. Okay, hang on. Let's think about these 2 digits now. They cannot add up to 13 anymore. There's no combination. And we know that so we know it must go there at least, possibly further. In fact, it can't be 5, 9, because that would be 14. So there's definitely a 2 in there for certain. Yeah, okay, it can't be 2. That's lovely. It can't be 2, 9, because then you've still got 2 more to find, and you can't put another 2 in the same cage, and you can't put 2 1s in the same cage. So this is 2, 5, I think, which makes this 9. 9 puts a... That's 3 in the corner. That's 3 in the spotlight, losing its religion. How does it know? How? How does it know that's a 3 in the corner? Because as far as the puzzle's concerned, does somehow the puzzle know that this is the grid? I don't know. That's very weird. I mean, it's very clever in whoever's made this into the software. That's really weird. Okay, you can't repeat 2 in the same cage. This is 6. 9 would be too much. So that's 6, and that completes the 24 cage. 6 is putting a 4 here. These index each other. So that this 45 cage definitely goes there. It's already had 3 in it. So let's take the 3 out. So this is 5 or 7, either indexing itself or putting a 5 here. I don't know what that means, I'm afraid. What else could we do? That's not 4 anymore. That's not 4, so that suggests we've got to put 4 here, which is putting 9 here. That's another bonus, isn't it? It's a bonus that hasn't done. Okay, that's 4, which is putting 2 here. We could have got that from Sudoku. So this is a 3-7 pair. And somehow or other we're meant to be able to resolve this, and I don't know what to do. In the bottom row, that digit is now 8 or 9. It could be indexing itself, or it could be putting a 9 here. So I suppose there is a 9 in this domino. And I don't see what to do with that. That's not 6 anymore by the dint of this 6. If that's a 1, oh yeah, it puts 8 there, that's okay. That can't be a 6 actually, that cell I've just looked at. That's 1 or 8. Indexing 1 into either of these two positions. Have we got any more self? No, we haven't. Oh, so it must be the cages, I think. Somehow it's going to be the cages. Right, here's a tiny point which I like. This orange cage is going there. And the way I've just seen that is I imagined it going here. Now I know it's already had a 4 in it, so if it goes there, it would have to then go there. But remember, if it goes here, this can't be a 3. So this is a 5-7 pair within orange, so orange couldn't go to that square because that would repeat that digit within orange again. There would be too many 5s and 7s. So I think, given that orange never goes there, orange always goes here. And you might say, well, that's great. Okay, so again, I'm going to do that again. Orange has to go here now for exactly the same reason. Orange could go there. It could go there, but that's still not 9 cells of orange. Orange can never go into 3s and 4s, so orange definitely goes here. So Sudoku might be our friend. Oh no, it doesn't work. I've already got 3, 4 and 9 in this. I was thinking this digit might be restricted by Sudoku, but I don't think it is. 2, 5, 7, 8. Indexing a 7, isn't it? So 2, 5, 7 indexing itself, 8. It can be all those things. That's quite ludicrous. Oh dear. 1, 2, 3, 4, 5, 6, 7, 8. Still has to go one more square. I'm not sure where that would be. Golly gosh, okay. Okay, so maybe it's where blue goes next. So blue can't go here, I'm noticing, because it's already had a 6 in it. Blue can't go here, can it, because of the weird grid furniture at the start. So blue either goes there. My phone's buzzing, please. Oh, that's... Oh, okay. Okay, that's the garage. I thought they were going to be calling me to say, okay, yeah, your car's ready. No, the inspection report has been sent via email. That doesn't sound good, does it? Okay, anyway, all right, so could it go here? Okay, what digits does blue need? It needs 2, 3, 4, 7. What's difficult for it to get in that panoply? It can't get that 2. Oh, yes, that's the question, actually. Sorry, okay, I could have got there earlier if I'd thought about it in this way. But this needs a 2 in it. Now, if we double-click the 2s in the grid, let me just think about this. Okay, so there's a 2 in one of those, but this is orange. So we'd have to... Oh, hang on, let's go back. So if we're getting a blue 2 from box 9, it has to be there. And that's too far away. We've only got 4 cells more of blue to get. So it's not that one. It's obviously not these. It's not that one. That's too far away. It's not this one by grid furniture. So that is a blue 2. Now, does that help, though? Does that mean that's blue? It doesn't really, does it? Because those 2 could probably be blue. Although, no, blue has had 8 and 9 in it. Okay, so blue's had 2 in it. It needs 3, 4 and 7. Oh, 3, 4 and 7. It's probably those. But that could perhaps be its... no. 3, 4 and 7. Okay, which is its 3? Because it's not that one. That's way too far away. If it was this one, then we've only got 2 cells left to connect blue up, and we'd have to take 2 4s to do it. Or we only need 1 4 and 1 7, so that doesn't work. So blue's 3 is that one. That's not blue. We've got to try and remember that. 1, 2, 3, 4, 5, 6, 7. I've got 2 more digits to find, and they are 4 and 7. So this, where's the 4? It can't be that one now, because then we couldn't put 7 in blue. So it's definitely that one, and blue needs a 7. And where's it getting it? Oh no, it's not either of them, because the 3 isn't connected. So it's that one. That's beautiful. What lovely logic. So 7, 9, 8. The 7 is in the correct position. The 9 and the 8 aren't. Now, does that help me with my Sudoku? Yes, it does. So 9 goes... Oh, that's self-referencing. It's not the ones we want. It's the ones that actually do things are the ones we want. Right, these squares now, by Sudoku, are 1, 6, 7. So that's not 7 anymore. So 2, 5, 8 is it, these? Okay, let's get rid of our corner pencil marks and think again. Have we improved our knowledge about orange now? I suspect the answer is going to be not very much. That's not 6. 1, 6, 7. Oh no, come on. How do we do this? Do I know the order of those? I probably do somehow, don't I? If that is a 2s and 5s, they're indexing 3s. Yeah. Hang on. That I see. Sorry, look, I could do more with these. I hadn't spotted this. If that was a 5, it would put 3 here, but 3, because this cell became orange, it wasn't allowed to be 3 anymore. So that has to be 2, that has to be 5. So does that do things? It takes a few things out, doesn't it? 5 is indexing 3 into this position. Oh no, that doesn't leave behind anything good. 3 comes here, 7 goes here. This is index. Oh, that indexes 2. 7 indexes 2. Yes. Yes, okay, good. Okay, so we are learning things slowly about the world. This is a 1. So that's an 8. 8. Oh, the 8 and the 1 index each other. So, okay, and the 9 is self-indexing. 6. Oh, goodness me, I don't know. I don't know. Right, let's try. It's going to be this, isn't it? This is the only thing that we've got left outstanding. So this needs, it needs so many digits. It needs 1, 2, 5, 6, 7. 1, 2, 5, 6, 7, 8. What's difficult? 1, 2, 1. Where does, oh no, it could get a 1 here. Or that 1. 2, it could have either of those. 1, 2, 5. 5 could be here or here. 6 could be here. Or that's 1, 2, 3, 4, 5. No, or there maybe. 7 could be either of those or that. And what was the other one? 8, which could be that or that. Oh goodness. Okay, so the 6 it's going to get is that one or that one. I don't know which of those I prefer. I prefer this one, I think. That if that's a 6, that's a 7, that's a 5. Those are both digits that we would like to have in here. 7, 5. 7, 5. 8, 1. 2, 3, 4, 5, 6, 7. Oh, hang on, hang on. There might be a problem with that, not sure. The problem I'm seeing, which could be wrong, is that I quite want this digit to be connecting up. Well, I need to put 7 in, is what I'm thinking. If that's 6, that's 6. That's putting 1 here. So I now can't have another 1 in here. So I can't take this digit, can I? So where then do I get 7 from? 1, 2, 3, 4, 5, 6, 7. I've got 2 digits left to connect this up and get 7. And what I foresaw is this. I think 7 becomes impossible. I'm not certain. So if this is 6, and you might say, well, that could be 7. But there was a reason I didn't think that worked. Oh, maybe I'm wrong, actually. Maybe this becomes 7. Hang on, let me try and... I don't want to do this by what I would consider to be bifurcation. I thought I saw it, and now it's gone. So I'm going to go back and think about it again. If that's 6... That's 6. That's putting 1 here, isn't it? So this is definitely a 1, which means I can't connect this 6 up through this square. That is a problem. I've got 6, 7. I've got 2 digits to connect up, not that one. So I have to do those 2, I think. Now, if I do that, have I got all the digits that I need, is the question. And I didn't think I did, but I could be wrong. 5, 8. So I would need this to be the 1, wouldn't I? And it would be, because that would be the 6. So that's okay. I've got a 2, that's beautiful. I've got 3, 4. I've got a 5 here. I've got my 6. This would be 7. That would be putting 5 here. And that would become 8. But that 8 is making this a 7. And I wanted it to be a 6. And that is no use. Gosh, that's complicated. Is there a better way of seeing that? So if that's 6, what we're saying then is this is 5, aren't we? Because if it's 8, that needs to be 7. Yeah. Yeah, you have to actually look at this 5, 8 pair, I think. If that's 6, that becomes 5. That becomes 8. So 6, well, I mean, we showed it didn't work, but let's just work it through so we can see it for ourselves. The problem with this is that we get 2 5s here in orange by Sudoku, and that's no use. But all of that, in order to arrive at that, we also had to work out we couldn't come through the 1, which was not easy to do at all. So it's my belief that the way you get 6 in here, which, well, it must do something, is that one. So that's 6, that's 7, that's 6, that's 1. Now that's putting 8 into there, which puts 1 into here. These 1 and 6 are very good. That's 5, that's 8. So that's 7, that's 5. And we've still got the problem. We've got to... Well, no, I haven't. I've finished the puzzle, in theory, if this is correct. But I haven't filled in this cage. I'm definitely claiming that. I need a 1 in it. 1, 2, 3, 4, 5, 6, 7. I need a 1, a 2. And that's what I need. But how do I... I can't get that one because I can't go through a 2, so I get that one. How do I, which one of these is right? Ah, I don't like that. 2, 3, 4, 5, 6, 7, 8. Which one of these is the correct 2? How do we decide that? Hang on, let's just check. Have I indexed one digit correctly in every row, column? Oh, I was about to say no, I haven't got an indexer in that column, but I do at the top. So 5 is indexed correctly there. So I should have 1, 2, 3, 4, 5, 6, 7, 8, 9. They're sort of stepping down the grid, aren't they? I don't know. Is this right? Will it even know? It is right. Good grief. Gosh, it's been around for a year. I mean, it's a brilliant puzzle. I don't know if I know which of, I don't know if even I'm meant to know. Or perhaps it's not the puzzle to know. Perhaps the puzzle is to fill the Sudoku digits. I don't know. I don't know. I'm going to go off and ask, and I might change the rules depending on if this last point is ambiguous. I might fiddle with the rules just so people aren't left in the position. I think I am. I think this is correct. Well, the solution's correct. And it's an utterly remarkable creature. This remarkable creature, because well, just think about it. It's bonkers that you can do this. That you can, with a couple of rules, just give a 3x3 box and specify a 9x9 Sudoku uniquely, findable by a human, if you'll permit me to claim that honour. I absolutely love it as I love it as an idea. I love it as an execution. I'm a little bit concerned that the rules could be slightly clearer on this bit. Which one of these I'm meant to take? I don't think I know from the rules, but I could be wrong. But Frippe, that is quite something. One of the most original things I've ever solved on the channel, and I loved it. And now I will go and investigate how much the garage is going to cost me. Wish me luck. And let me know in the comments how you got on. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.